So our next speaker is Holly Shulman.
Hello. So I will be going very quickly through this about exploration of scalable methods to fabricate synthetic lunar minerals for engineered regolith simulants. And thanks to my co-authors that are listed here. Next slide, please. So this is very different than the other talks. I'll tell you my goals and the scalable methods and laboratory results. This is all Earth-based. Next slide, please. Looking at developing synthetic lunar minerals instead of mined minerals. And the ultimate goal is that we have sufficient materials for large-scale construction experimentation. My focus is on microwave densification and sintering, but these materials would be available for everyone and to be able to make blends that are targeted to different regions. Initially, I'm focused on the highlands. Okay, next slide, please. So there are two main methods that are scalable. These are just ceramic processing methods. So, I hear people talk about, grains and soil. Well, from my viewpoint, these are ceramic materials and also mixed with glasses. So it's very typical that we are making minerals and different blends intentionally at a large scale. This is a typical ceramic processing. One of the methods is a solid state reaction that we also call the mixed oxide method. And we use oxides and sometimes carbonate powders. We mix them, we heat them, and we form our final mineral that we're after. So I want to point out that the powders that you put in will very often control the final particle size that you get out. And typically you want to go to fine powders so that we can react them more easily. But if we want larger grains, then we might either need to use larger starting powder or go through another process where we start to grow the grains to get to be able to control particle size. So typically these are fine powders. It's really important to avoid reaction with the container, and I point this out especially here because in the lab we might use a platinum crucible. It's quite common, then you don't have to worry about reaction, you can go to high temperatures, you can even melt. And that is something that I avoided in all of my lab scale work in order to be able to focus on things that are really scalable. So we'd find out about what types of materials we can put our powders in. So one method is a batch kiln, and those powders go into saggers, which is really just a large-scale crucible. And those are designed to have flow through. So at the top, it might be fluted, and you can have gases that come in and out. And it's typical to need to do that in this calcination process. Another is a rotary kiln, and those are powders that go in a large rotating tube. And if you go to the next slide, please. I'd like to point out that you don't have to set up a manufacturing facility for these. There's plenty of places that will do toll firing or toll calcining. And this is just one example, Harrop Industries. On the top right, you see the elevator kiln. So that's a batch furnace, and you can see those saggers. That gets loaded in, and in this kiln, the furnace is actually on the top. It's just an easy way to access. The other method, the rotary, is actually continuous. So you can put powders in a continuous basis. And one of the advantages is the tube is turning, so you have good mixing as you go. And you can go to high temperatures if you make sure that you use a tube that doesn't react. Okay, next slide, please. So another method that's very different, but it's also used at large scale, and it's probably the most prevalent method for being able to make minerals and certainly for abrasives. And in this case, you have your powders go in to a large vessel, which is usually made out of graphite, and there's graphite electrodes in there. And with a high voltage, an arc is generated between those electrodes to very high temperatures. So the powders going in are reaching like greater than 3000 C and forming a melt. The difference between this method and the mixed oxide is that this cools and you form a big boule or a big solid mass. and of whatever mineral it is that you targeted with your composition. And a benefit of that is you can crush it and mill it to different particle sizes and particle size distributions. This can be done in a lab scale, 5 to 10 pounds. A pilot scale is on the order of 200 pounds. And a typical production system would be about 8,000 pounds. So these are easily scalable. And a company, Washington Mills, has the biggest facilities, and they will also do toll firing work. I want to point out there's something else really interesting about this method. You can blow gas into the melt as it cools, and it will form hollow spheres or bubbles that they can control to somewhere between 500 microns and 2 millimeters. And they'll do this typically for some of the materials that are hard to crush. A lot of these ceramics are super hard. And so they blow in these bubbles and makes it easier in the crushing phase. But we might want to do that to be able to control some of these microstructures and make some things with jagged edges, or be able to make pseudoagglutinates this way. So next slide, please. So we're targeting highlands, and if you look at this from the Lunar source book, I put this together in a different table, that plagioclase, pyroxene, olivine, plus glasses that are pretty much made from those minerals will constitute from 96 to over 99% of the regolith in the highlands. And so it's not that the last little bit of materials aren't important. They can be critical to both dielectric properties and also sintering. It's just that if we make blends out of these materials, we can then add the other bits that we need. And being able to control these blends, we're able not to just have one simulant that we're trying to match that's mined. We can bound the behavior by changing these compositions in a controllable way. So the plagioclase is predominantly a northite, and that makes up a large proportion of what's in the highlands region. And the pyroxene, there's two different types that we're representing here using diopside and enstatite, and then olivine. And I'm using X-ray to give feedback on did we hit those mineral targets. You can go to the next slide, please. And I'm starting with the easiest one, I know I'm out of time, which is olivine, which is already naturally available and commercially available. Next slide, please. And a northite, which we were able to demonstrate both in the solid state method and the arc electrode method. Very easy to make this stuff. A little bit of minor phases, needs a little tweaking, but we know how to do that. Next slide, please. Diopside, also very easy. We made it solid state method. No reason it shouldn't also work well in the arc electrode method. So we're not worried about our diopside. So these are all things that are done. We've demonstrated it. We know how to scale up. Next slide. So I just want to tell you a little bit about our problem child, and that is enstatite. It is the most complex of the pyroxenes because it has so many polymorphs. So we're struggling trying to control that and get the correct one that is part of the lunar highlands. So if you go to the next slide, please, and maybe one more slide. So these are different enstatites that we're looking at different temperatures. If we go to too high a temperature, we definitely get out of the right phase field. But this is the correct phase, is orthoenstatite. We still have a little phosphorite in there, and that's not too bad because phosphorite would also be in the lunar material. What we don't like is the quartz or silica, but there is a process by which to get rid of that. But in the
You can go to your
meantime,
conclusions. That would be great.
okay, next slide. So that's it. You can read the summary and next steps, and we're basically working on enstatite and almost done. Thank you.
Thank you so much.